Up to this point, we have been compiling programs on our local systems, and they naturally were generating either x86 64-bit instructions or 80386 instruction, since that is the architecture of our machines. But as we know, the world is not limited to x86. Most mobile devices, tablets, and embedded systems use ARM architecture. Today, we'll explore how our C programs, which you used in earlier both sessions, look when compiled into ARM instruction set architecture. Specifically, what we'll do is we'll need following steps to be followed. So we have to install ARM cross compilation support on our Linux Ubuntu. We will use the same programs where one of them was addressing simple arithmetic and other one was talking about factorial. We'll compile both one by one into ARM assembly, and then we'll understand why linking ARM code into executable on x86 fails. Fine. So let us first understand how it works with how to install ARM GCC. Now, to compile for ARM on Ubuntu, we need a cross compiler toolchain, and we have to install it with this command. So let me open it. So what you have to do is you have to first write this command, sudo. I already did that, but I'm just writing for the sake of understanding for you peoples. Like, you have to first write this sudo apt-get update. Press enter. Then it will ask you for your root password. So you enter that password. Once it is done, next instruction that you have to apply is sudo apt install gcc arm, then linux, and then gnueabihf. Sorry, gnueabihf. This is also added into the lecture notes that you will be getting about this particular thing. Now, what I wrote here is like sudo apt install gcc-arm-linux-gnu executable abi and then hf. Okay. Now this installs the tool arm-linux-gnueabihf-gcc, which can take C program and produce ARM machine instructions instead of our x86 architecture. So I also have installed this one. So let us try working with the code. Okay, what are the code that we wrote earlier? Fine. So we know that we have written this code. So let me go to this code. Let us pick the first code that we wrote. This was with respect to addition, and we gave values as 10 and 8 in this case. And then we printed sum, we calculated sum, difference, and product. Correct. And then we printed the result. Now, how you compile this? So you have to write ARM dash Linux. So if you press tab, then it would be adding that part automatically. So then you take GCC. Fine. Right now I'm writing GCC. Then just write dash S. Okay. And then your program name. So fact.c. For the sake of generating the file name in this case, so this would be generating .s basically. So let us check. Okay. So now if I really see this, like if I write fact file fact.s, then it again is saying the similar thing, a similar source. But now if I open that file, it would be somewhat different. Okay, because the file format is different now. Now let us go below. Now you can see the instructions are completely different. And this is the file like fact.s. And this is what we see inside, that we see all ARM instructions, ARM instructions. Like for example, you would be seeing move, you would be seeing add, you would be seeing str, sub, mul, and so on. So here we notice that ARM style here, all operations are register based, R1, R2, R3, R4, R5, whatever. Unlike x86, memory is rarely accessed directly in arithmetic. And this is what the risk design principle, which we addressed earlier too. Correct. Now, let us say if I have to compare with my other code. So let me write, say for example, I will rename this. So I will write mv fact.s and I will write fact arm so as to so that we can understand .s. So this will be our arm file underscore arm.s. This would be our arm file. Okay, arm based assembly code. And similarly, if I try to now compile this code, now instead of this, I will be using my plain GCC to generate object code in 64-bit form. Now, if I open this code, rather fact.s, now let me see this. Let me show you this comparison. So I will add this terminal here, and I will open one more terminal, and I will try to write here about like the other one. So let's fact underscore arm.s. Now let us see the difference between both the files. Like if I see here, it is starting differently, but it is showing the same thing. Like say from here, it is showing the same thing. Correct. Similarly to what we see here, file fact.c, dot text, section dot ro data. Now this alignment is not added, but dot lc0 is used. Factorial is something. So here we haven't used anything, but it added /000 there. Then again text, so on. Then main syntax unified. Now, like this is the kind of change that you see with the code. Now, if I go to main, see the main difference. The difference in main function of this was x86 and this was R. Correct. So the style of writing assembly code or generating assembly code with respect to or from the compiler, what we did is we used C compiler only, GCC only, but just we used it as a cross compiler. We created that file for ARM, basically. Fine. Now, same code, the way that we did with this code, if I talk about our factorial code, okay, rather, if you see this was like I assume I opened it with fact because we compared with fact one, correct? So when we compiled the code, ultimately this was with respect to the fact.c. So now if I take the another code, like where we compiled, uh, the program was this. Yeah, this one, where we added two numbers, subtracted two numbers, and multiplied two numbers. So if I take that one again, so let me write here 1.c. Okay. Now we know that the file generated would be 1.s. And if we try to check the contents of 1.s, it would be again the similar kind of assembly code. Now it is just addition, subtraction, correct? Fine. Similar kind of instructions are there. Just the way to write, the philosophy is changing. Like earlier things were like where we are using memory and data directly extensively. Here we are relying heavily upon with the ARM, we are heavily relying upon the registers. Fine. So this is how the codes are shown, correct, for the both the cases. Like now, if I try to generate now, if let me rename this. So mv 1.s 1 arm.s. Okay, let me generate now my simple uh, assembly code for my Intel. So less 1.s. This is my code, and let me write here less 1 underscore arm.s. Now see the difference again. Like this is the code that we have. If I go below, this was main. You can see like let us go below here where the exactly operations are starting. These are the values that we gave 10 and 8. Now if we see here, this was for 10 for first variable. This was for 8. Now you can see here we are using memory RBP because of RBP. Here we are heavily dependent on registers. We are not referring to memory directly, and this is where the difference is. Correct. Now, again, if you notice, we are using similarly the way that the instructions used were like addition, subtraction. Way to write that instructions maybe like the what you can call it a mnemonic. Here we have add. Here we are having mul. Then there is a second say LDR add. correct? These are the instructions that it is having. Then subtraction is there. Okay, subtraction. Then multiplication is there. See the difference of even multiplication instruction. So if you see here, there is IML, and both of them, like most of these instructions are taking two operands. But here, sometimes there can be three operands, there can be two operands. Okay, so this is how your ARM code looks like. Now, if I try to, let us say, like if I try to generate an object code instead of dash s, if I'm writing dash c, and now I know that my 1.0 would be generated, right? So if I write file 1.0, then it is telling me that, now see, earlier we had what? We had ARM. Like for example, let me write here GCC dash. Okay, we will create an code only for 64-bit code only. Now here I will write dash o and my file name, uh, like say for example, arm1 dot c dot o. Okay, dot o, and I am writing dash c. Let us see like if we can get this file arm1 dot o, which is not arm file rather. One can see here the difference. ELF 64-bit relocatable, and here we saw its architecture to be x86 64, and here we can see that it is ARM. Now similarly, if I try to generate its executable, instead of writing this, if I remove this dash c and if I write just 1.c, if I check this ls-ltr, it is generating me a.out. If I try to find out what is a.out, again you can see that it is ARM. If I do it here again, like instead of dash c, I'm removing it. Okay, and here I am writing ARM1. We know that this ARM1 we are getting here it with x86 64. So if I write now file and this ARM1 only just, then you can see it is 64-bit LSB executable, and instruction set architecture is x86 64, and here we are having ARM. Now if I try to execute this ARM executable here, like whatever I got. Okay, now okay, let me recreate this. Sorry, I executed dot/a.out. Instead, I should have executed arm1. Now, if I execute this, the output is shown. If I do the same thing with respect to this a.out generated here, it says cannot execute binary file, exec format error. That means it is giving us error. And this error means what? The file we got a.out, correct, is a real ARM binary. And our machine, our system CPU is x86 64, and the CPU simply does not understand the ARM instructions. And this is a very important lesson. Executables are architecture dependent. On the other hand, if you see .s files, the assembly code, are just text, so we can always generate and read them. But important to note here, executables can run only on machine hardware. Now, if you really want to execute this, then definitely you can install an emulator like something called as KMU. Okay, so you can use that definitely, but our goal is not to understand how that emulator to be used for execution. Our goal is to understand only how the instructions and architecture is used. So to summarize what we did here, we installed the ARM cross compiler on Ubuntu. We wrote two programs. Rather, we took them the earlier one. One was addition, subtraction, multiplication, another one was factorial. We compiled both using arm-linux-gnueabihf-gcc-s to produce assembly file. We analyzed ARM instruction like simple, register based, and mostly they are risk oriented. And we learned why executables cannot be linked and run on x86 hardware, because the instructions are incompatible with our CPU. And this demonstration shows us that true hardware dependence on the instruction architecture. The same C program produces different assembly codes when compiled for x86 versus ARM. Thank you.